These are your 10-2A notes, simplifying radical expressions. And so this is the intro to what we'll be doing this chapter. We're going to actually take 3 days to go over concepts in section 10-2. We're skipping 10-1 completely. That's actually graphing a radical equation. So first of all, start off with a definition. What the heck is a radical expression? It's an expression that contains a square root. So if you recall from way back in September, an expression is different than an equation. An expression doesn't have an equal sign. So it's just like a number, but it's just kind of a little different number. Okay, and then I have the parts of a radical expression. So this is the whole thing is called the radical. Okay, it's important to understand the parts and what they're called because when we talk about the rules, you have to understand what they are relating to. So this whole thing is called a radical. The number underneath the radical sign is called a radicand. And then the little number that sits on the outside of the radical sign, right on that little foot there, is called the index. Now, we're going to primarily work with square roots, but there is such a thing as a cube root. And so a cube root would have a little 3 sitting there. And the cube root, let's say, of 8 is asking, what do you multiply by itself 3 times to equal 8? And the answer is 2. So when you answer these things, it's kind of hard to understand what they're saying. So when I ask for the square root of 16, there is no little 2 on that foot. It's understood that there's a little 2 there, okay? So you probably won't see a 2 here at all. But what they're asking for is what do you multiply by itself to give you 16, and the answer to that is 4. Okay, so that's what we're going to be working on, is simplifying these things. Now, we worked on them a while back, and we worked with the nice ones. We used a calculator. We could push buttons. But more importantly, in this chapter, we're going to work with the ugly ones and how to give the exact value of these ugly numbers. So just to review radicals, we're going to simplify the following perfect squares. So look at your calculator. Try to find that radical button. Okay, a lot of times if you have something that's like an x squared on your calculator, a button like that, right above it will be the square root. It might have an x in it. It might have a y in it. Opposite of the caret button sometimes too. That one's usually for bigger roots. Since these are all square roots and we're only going to concentrate on square roots, it's usually this symbol that we want to access right above the x squared. So you usually have to hit like a shift or a second key to access that. So just work with your calculator and try to get the square root of 25. But what this is actually asking is what do you multiply by itself to equal 25? And the answer is 5. Part B, it's asking what would you multiply by itself to get 121? And the answer is 11. So you should be getting these numbers when you use the calculator correctly. And what do you multiply by itself to get 196? And the answer is 14. Okay, so I'm hoping as we go through these that some of these are going to become just second nature to you. I'm hoping you know the square root of 25. So in this process, some of those radicals are not perfect. For instance, if you go ahead and type the square root of 10 inside your calculator, there are 2 numbers that multiply that will equal 10, but they're ugly. They go on forever and ever. They're not a whole number. And so the square root of 10 is considered an irrational number. It goes on forever. It doesn't repeat. And so what we're going to work with is if there's a way to write them in a simplified form other than that ugly decimal. The square root of 10 is actually as simplified as you can get. But we were going to look through this checklist to see, and I want you to read, we're going to refer back to this checklist throughout this chapter. So the first part in wondering if a radical is simplified or not is that there are no perfect square factors of the radicand. If you can find a perfect square living inside the radicand, then you need to take it out. So remember, the radicand's the number underneath the radical sign. Maybe the number itself is perfect, then it needs to be simplified. You cannot leave the square root of 25 as the square root of 25. You've got to simplify it to 5. But there's also problems where you can pull a little bit of a perfect out. You cannot have fractions under the radical sign, okay? No fractions under the radical sign. And then it's simplified if there are no radicals in the denominator. So no fractions, no radicals in fractions under the radical sign, no radicals in the denominator, and you can't leave perfects under the square root symbol. Okay, so we're going to refer back to that checklist throughout. The one property or rule that we're going to use today, remember a property is just fancy for a rule, is the product property. So product implies multiplication. Property remains, it says rule. So this is the multiplication rule of square roots. And it's basically a very short definition. If you have some product underneath the radical sign, you are allowed to break it apart into its factors. But I like this rule because this rule is actually true both ways. Anytime you have an equal sign, it's true both ways. So if you have two radicals being multiplied together, you can actually multiply them and put them underneath one radical sign. So I like to look at that as here, if I had the square root of 20, I can actually rewrite that as a square root of 2 times the square root of 10. Or the square root of 4 times the square root of 5. And if I had the square root of 2 times the square root of 10, I could put that back together and call it 20. Or I could put 4 and 5 together and call it 20. So this is the one rule we're going to concentrate on today. Before we do that, let's go ahead and go through our first 15. I'd actually like it if you had 20, but the first 15 perfect squares. So 1 squared is a tricky one because everybody forgets about 1 squared, but it's perfect. 1 times 1 is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. Then you've got 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. So you should be set. This is a nice list to refer to as you're working with your homework today, because you really won't get any bigger than 15, I'm assuming. So now you have a list of all your perfects, and not only do you have the list of perfects, you have the number that they're perfect of. For instance, if I look at 49, I know that the square root of 49 is equal to 7. So not only do you have the 49 that it's perfect, you have the base or the radicand that it's perfect of. All right, so we're going to go ahead and we're going to simplify these non-perfect radicals. So using your calculator, if you type in the square root of 12, you're going to get an ugly decimal. I don't want ugly decimals, and I'm telling you next year when you're in geometry, they're going to know that you've had this, and they're going to want you to use it. It's a more exact approach to radicals. So it's a way to write these things without rounding, without having to use a calculator. So I want to make sure that you understand the process. If any of your calculators do this process for you, they will be taken away for this quiz. So I just want you to know that if you found a really cool button and you're like, oh yeah, my calculator does that, you will not be allowed to use that calculator on the quiz. So the square root of 12 is not perfect. So when I put in my calculator, I get a decimal. So now I have to reply and think about my checklist. And my checklist says, are there any perfect factors, any perfect squares inside the radicand? So I look at that square root of 12, and I think about my list of perfects, and I'm seeing a 4 in there. And so I want to break the 12 into factors, the square root of 4 times the square root of 3. Now, I know you can break 12 into 6 and 2 as well, but that doesn't do us any good. I'm going to just do it off to the side to show you. When you break 12 into the square root of 6 times the square root of 2, yes, that's true. They are equivalent. But square root of 6 is not perfect, and the square root of 2 is not perfect, so it doesn't do anything. So we want to stay away from factors that aren't perfect. So what I always practice is you put the perfect one first, and then you put the non-perfect one after it. And there's a reason for that. So we're always going to try to do that. We're going to do perfect radical times the non-perfect. If you set it up that way, the perfect radical will turn into a whole number. So you're going to ask yourself in the next line, what is the square root of 4? Well, the square root of 4 is 2. When you ask about the square root of 4, you're asking, what do you multiply by itself to give you 4? The answer is 2. The square root of 3 is ugly. And so you get 2 times the square root of 3, and you are done. The square root of 12 is equivalent to 2 times the square root of 3. Now, you could check your answers using your calculator. When you type in the square root of 12, you'll get an ugly decimal. And then when you type in 2 times the square root of 3, you'll get the same exact ugly decimal. Okay, so let's try part B. Part B, get the square root of 18. It is not perfect, and so I'm going to go through my list of perfects. I don't care that you can pull something out of 18. I'm only concerned about that list of perfects right here. So when I look at this list of perfects, and I'm trying to pull something out of 18, a lot of these numbers are too big, but I do notice that 9 goes into 18. So I am going to rewrite the square root of 18 as the square root of 9 times the square root of 2. The square root of 9 becomes a 3, and the square root of 2 remains. So I want to see that in your work. Okay, I physically cross off the square root of 9 because I want you to understand that it's being replaced with 3. It's equivalent to 3. That's what the square root of 9 is. And so I write the perfect number that's going to change out front, and I leave the ugly number in the back. So 3 root 2. 90 also has a 9 living inside it. Okay, I know 90 has a 2 living inside it and a 3 living inside it and a 4 and all that stuff. We don't care about that. What I worry about is just the perfects. And so I look at my list and I say the square root of 9 times the square root of 10. The square root of 9 becomes a 3, and the square root of 10 stays. So I have 3 root 10. Square root of 25 is perfect. It's already perfect, so you can't write it as a perfect and a non-perfect. You can just answer the question, which is 5. Square root of 450. Okay, well, I need to look at my list. And when I look at my list, that's a pretty big number, 450. So when I look at my list, I really don't want to be looking at it from the beginning to the end because those are smaller numbers. You want to take out the largest perfect value that you possibly can. And so I'm looking at that and I'm thinking 450. I know that 9 goes into 45. And I'm thinking that maybe out of 450, there might be some extra stuff. So I'm going to start with 9. I'm going to pull a 9 out and then see if I have to go from there because I want to show you what happens if you don't pull the biggest amount out. So I'm going to rewrite this. So I know 9 goes into 45 5 times. So this would be the square root of 9 times the square root of 50. The square root of 9 becomes 3. So now I have 3 times the square root of 50. But when I look at 50, I realize there's another perfect possibly living inside there. And I've been doing this so long that I know that the other perfect that I could pull out of 50 now is 25 times 2. And so this happens if you don't take the biggest amount out first, then you just keep pulling them out. So it's telling me that I should have taken out a 225. 225 would give me the 450. So when I take this 5 out, this is all multiplication. Anytime you write those numbers on the outside, it's all multiplication. So I have 3 times the square root of 25, which is 5. So now I'm going to multiply those two together because there's a 3 on the outside and a 5 on the outside. So I'm left with 15 root 2, or 15 times the square root of 2. So that's showing you if you don't take the biggest amount out. Now, I can show you right next to it, if I would have taken the right amount out, it would have been 225 times 2. 225 times 2 is 450. The square root of 225 is 15, and so now I have 15 root 2. So you get the same exact answer, but look at how much less work and how many less errors you might make by doing it right the first time. So it really does pay off to to take the time to make sure you're taking the biggest amount out. But sometimes you don't know what the biggest amount out is. Okay, so sometimes you could only see the 9, and then you see the 50, and you realize, oh, yep, there's a 25 living in there. So it's okay. Both ways are okay. For 45, well, we already did that with the 9. So we're going to go ahead and do square root of 9 times the square root of 5. The square root of 9 is perfect of 3, and the square root of 5 just remains. Okay, so the majority of your answers today are not, or tomorrow's homework, are not going to be perfect. All right, let's talk about variables. We're going to throw some variables into the mix. So a square root of a variable, the variable is a perfect square if it has an even exponent. So the variable will be perfect. Variables are perfect if they have an even exponent. So looking at A, remember when you take the square root of something, it's saying what do you multiply by itself to give you x to the 4th? And the answer is x squared times x squared. So the answer to this is x squared. It's perfect. It's beautiful. Okay, if you look at this next one, part B, they're all perfect. What would you multiply by itself to give you m to the 4th? M squared times m squared. What would you multiply by itself to give you n to the 6th? N to the 3rd. And what would you multiply together to give p to the 8th? P to the 4th times p to the 4th. Remember, when you multiply variables, you add their exponents. Now, part C, not everything is perfect. The A is perfect, but the B is not perfect. So what we're going to do is, if it's even, I'm going to rewrite it just like we did with the numbers. I'm going to rewrite variables. So I'm going to rewrite a squared. I'm going to separate it. That's perfect. I'm going to pull out the perfect b to the 4th because it's even, it's perfect. But then if I take b to the 4th out, I still have an extra b. There's your 5 b's. And then we're going to simplify. So these first two are going to give me nice, perfect answers. The square root of a squared is a. The square root of b to the 4th is b squared. And then the square root of b just remains. That's your final answer. For part D, same thing. These are both non-perfect variables because 11 and 13 are odd exponents. So I'm going to rewrite it as d to the 10th, an even exponent that I know is perfect, times d to the 1st, or just d. And then I'm going to rewrite that e to the 12th times the square root of e. I need to see the step in your homework. The perfect and the perfect and the non over and over again. And so what do you multiply by itself to give you d to the 10th? D to the 5th. And what you might want to do is maybe leave a space and your radical, okay? Because I'm going to have some stuff that goes inside and outside. So I always like to start these off with a big space. I even make a line. This is all my beautiful perfect stuff. And then inside the radical is all the ugly stuff that remains. So d to the 5th stays outside. It's nice and pretty. Square root of d inside. It's ugly. E to the 12th goes on the outside. Now, when it goes on the outside, it transforms. It's beautiful. Okay? E to the 6th, and then the inside E. I like to call this Beauty and the Beast. Okay? The beauty gets to go outside. It transforms. Think of like a butterfly. Beautiful. It transforms, but the beast stays inside, right? Beauty and the Beast. The beast of these numbers stay inside. They're the ugly, irrational numbers. All right. So now, let's take that concept and let's put those two concepts together. We're going to do numbers and variables together. Some of the numbers are perfect, some of them are not. Some of the variables are perfect and some of them are not. So we're going to separate them into each of their own little categories. So the square root of 144 is perfect, so I'm just going to rewrite it. Actually, all of this is perfect, so I'm going to take that back. And 144 I recognize as 12, and then those two are even. So I don't really need to break this into perfect and nons. They're all perfect. The square root of 144 is 12. The square root of b squared is b. And the square root of c to the 4th is c squared. And that's all done. Nice and cleaned up. Looking at part B, 81 is perfect, but I need to rewrite this a cubed. So I'm going to rewrite square root of 81, just leave it as the square root of 81, times the square root of a squared times the square root of a. So I broke up the perfect and the non for the variable. I'm going to leave a space out in front and make my radical. That way I can work right down the line from left to right. So I'm going to start with 81. The square root of 81 is 9, goes on the outside, it's gone. I'm going to move over to the next term. The square root of a squared is a on the outside. It's done. And the square root of a now goes underneath the house. So what's nice about having space out in front and then your radical, you can work straight across from left to right through the whole problem and not have to worry about where you put it. You can just put it there. If it belongs out in front, you put it out in front. If it belongs in the radical, you put it inside there. So yeah, I have some awkward spaces, but it's okay. 9a times the square root of a. Or you could clean it up if that bothers you. And there you have it. Okay, looking at part C, 72. I know a lot of people think of 9, but actually the biggest number we should take out of there is 36. So this time my variable is perfect, but my number is not perfect. So I'm going to break 72 into 36 times 2. This just work takes practice. I got them in my head. Eventually you guys will get them in your head. But work with your calculator. Take that list of perfects and see which ones divide into 72. And then I'm going to leave d to the 8th just as that. So I'm going to have my space out in front. I got my radical. So the square root of 36 is 6 on the outside. It transforms. Square root of 2 goes inside the house, or inside the radical. Square root of d to the 8th becomes d to the 4th on the outside. When the number goes on the outside and is perfect, it loses the radical sign. That's the whole definition of a perfect. It becomes a whole number. All right, last example here. 8 is not perfect, but I know that there's a perfect living inside it. 4. F is perfect, and then G I have to break down because it's odd. So I'm going to rewrite 8 as the square root of 4 times the square root of 2. I'm going to leave F alone, square root of F to the 8. And then I'm going to rewrite G as square root of G to the 12th times the square root of G. I have my line for all the beautiful stuff out in front, and I have my radical for all the ugly irrational numbers. So square root of 4 becomes a 2 on the outside. Square root of 2 ends up going inside the radical. The square root of F to the 8th becomes F to the 4th outside. The square root of G to the 12th becomes a beautiful G to the 6th on the outside. And the square root of G is the leftover irrational part. That right there is the simplified form of that radical. Okay, so we're going to do a whole worksheet of these tomorrow in class. So the lesson summary, I want you to explain to me if x to the 5th is a perfect square or not. Just explain yes or no and why. And then your simplification problem is a 56, x to the 1st, y to the 10th, z to the 5th. Good luck.